Study on the relationship between kinematic viscosity, density, and temperature of lubricating oil POW. Abstract using the oil products kinematic viscosity tester and petroleum products density tester, the kinematic viscosities and densities of 5 POW oils with different initial viscosity were measured in the range of 30 degrees C 110 degrees C. The relationship between viscosity, density, and temperature of POW oil was analyzed. The relation on viscosity-density-temperature of POW oil was established. The results show that the viscosity and density of POW lubricating oil decrease with the increase of temperature, and the higher the density of POW oil, the higher the kinematic viscosity of POW. The newly established viscosity-density-temperature formula can better describe the relationship between viscosity, density, and temperature of POW oil in the range of 30 degrees C 110 degrees C. This formula can be used to predict the viscosity of POW oil in a certain range of temperature. Keywords: POW, kinematic viscosity, density, temperature. Introduction. POW oil is widely used in all fields of industry because of its comprehensive high-quality performance. As a quality index of lubricating oil, viscosity has influences on oil film thickness, bearing capacity, mechanical efficiency, and friction heat generation, etc., and has become an important factor affecting the service life of equipment. Therefore, it is of great significance to study the viscosity of lubricating oil. Domestic scholars have conducted many researches on the viscosity of lubricating oil 1-3. Lijun analyzed the effects of temperature and pressure, molecular weight, and molecular structure on viscosity of lubricating oil 4. Liang analyzed the influence of constant bath temperature, viscometer viscosity constant, viscometer cleanliness, viscometer installation state, sample cleanliness, and other aspects on the measurement results of lubricating oil kinematic viscosity 5. In 2016, Lijun Li studied the relationship between lubricating oil density and viscosity, and proposed a new viscosity pressure relation formula based on density to obtain viscosity 6. Reference 7. Introduces an applied research method for viscosity conversion of lubricating oil at different temperatures, which can realize the rapid calculation of viscosity index of oil with pour point greater than 50 degrees C 7. Abroad, the Soviet Union scholars studied the influence of viscosity temperature characteristics of lubricating oil on power loss of automobile transmission system 8. Seaton CJ studied the relationship between fluid viscosity and temperature 9. D. Nazevic proposed a mathematical model for the dynamic viscosity of mineral oil in a hydraulic system, varying with temperature and pressure 10. Baer S. studied the variation of the viscosity of various lubricating oils with temperature and pressure 11. At present, the research on lubricating oil viscosity mainly focuses on the influence factors of lubricating oil viscosity, as well as the empirical formulas of temperature viscosity, temperature density, temperature pressure viscosity. The relationship between viscosity density temperature of lubricating oil has not been studied. In this paper, the viscosity and density of POW oil and the relationship between viscosity and temperature are studied. The viscosity-density-temperature model of POW aviation lubricating oil was established. 2 experimental devices and methods. The test samples were 5 POW oil of different viscosity provided by Sinopec Lubricant Company Tianjin branch. The kinematic viscosity at 40 degrees Celsius is 32 mm2/s, 48 mm2/s, 68 mm2/s, 110 mm2/s, 125 mm2/s. In order to explore the relationship between kinematic viscosity, density, and temperature of POW oil, we first tested the kinematic viscosity and density of the above lubricating oil samples at different temperatures with petroleum product kinematic viscosity tester and petroleum product density tester. A kinematic viscosity testing device and method. The measurement of kinematic viscosity is performed by SYP 1003-6 Petroleum Products Kinematic Viscosity Tester. Figure 1 is the device diagram of petroleum products kinematic viscometer, which is mainly composed of temperature control box, constant temperature cylinder, constant temperature medium, heater, agitator, stopwatch, and viscometer. CF8 FF44 56 F2D 2325 EDB17873782B149. Fig 1 Motion Viscometer for petroleum products. During the test, pour the constant temperature medium into the constant temperature cylinder, turn on the heater and set the test temperature. When the temperature of the constant temperature medium reaches the test temperature, the viscometer loaded into the sample is placed vertically in the constant temperature medium for 15 minutes to measure the time of a certain amount of lubricating oil sample flowing through the capillary tube of the viscometer. Repeat the measurement 4 times. The kinematic viscosity of the sample at the set temperature can be obtained by multiplying the average value of the time obtained at least 3 times by the viscometer constant of the selected viscometer. The kinematic viscosity data of the lubricating oil measured by the above device is shown in Table 1. B. Density test device and method. The determination of the lube oil sample density is done by the petroleum product density tester. The structure of the density tester for petroleum products is shown in Fig 2. Fig 2 Density tester for petroleum products. During the test, the constant temperature medium glycerol is poured into the constant temperature cylinder, and the constant temperature is set through the temperature control box. Pour the sample into the sample bucket, put the sample bucket into the constant temperature medium, make the liquid level of the sample lower than that of the constant temperature medium, and maintain the constant temperature for a certain time. When the temperature of the lubricating oil sample measured by the thermometer reaches the set temperature, select the appropriate densitometer and place it into the sample in the sample bucket. After the densitometer stabilizes, read the scale on the densitometer that is tangent to the liquid level of the sample. This reading value is the density of the sample at this temperature. See Table 2. 3. Analysis of test results. After collating the experimental data, the density-viscosity relationship of POW lubricating oil at 30 degrees C, 50 degrees C, 70 degrees C, 90 degrees C, 110 degrees C was obtained, as shown in Fig 3. Fig 3 Relationship between dynamic viscosity and temperature of lubricating oil with different viscosities. As can be seen from the figure, the density of lubricating oil with the same kinematic viscosity gradually decreases with the increase of temperature, and the trend of density reduction is approximately linearly correlated with the trend of temperature increase. At the same temperature, the lubricating oil with high kinematic viscosity has higher density, and with the increase of kinematic viscosity, the trend of density increase gradually decreases. For determination of viscosity-density-temperature relationship, use first optimization software. Regression analysis of the above experimental data was carried out by using Macquarie method. The fitting formula between kinematic viscosity density and temperature is obtained as follows. In the formula, T is temperature, is the density of POW oil at T. P1 equals minus 40.168. P2 equals 12.869. P3 equals 7.905. P4 equals minus 23.451. P5 equals -8.01868 G102. P6 equals 7.741. P7 equals 1.091997 G102. P8 equals 1.6955976 G104. Formula 1. Reflects the relationship between POW lubricating oil kinematic viscosity, density, and temperature. Population correlation coefficient R equals 0.99205. The relationship of the three is shown in Figure 4. Graph 2. Fig 4 Comparison of calculated and tested values of kinematic viscosity density temperature relationship. In the figure, the grid represents the predicted value of formula 1, and the white squares represent the test data points. V. Error analysis. Table 3.7 shows the comparison between the calculated value and the test value of formula 1, when the temperature is 30 degrees Celsius, 50 degrees Celsius, 70 degrees Celsius, 90 degrees Celsius, and 110 degrees Celsius, respectively. It can be seen from the above table that the calculated value of viscosity-density-temperature relation is close to the experimental value. 6. Conclusion. In this paper, the kinematic viscosity and density of POW oil samples with different initial viscosities were measured at different temperatures and the experimental data were analyzed. A functional relationship between POW oil viscosity density temperature was obtained by fitting test data. The following conclusions can be drawn. 1. The viscosity and density of lubricating oil decrease with the increase of temperature. At the same temperature, the density increases with the increase of kinematic viscosity, but the increased trend decreases gradually. 2. The equation of viscosity-density-temperature function is obtained. It can describe the relationship between viscosity density and temperature of POW oil. The kinematic viscosity of POW lubricating oil in the range of 30 degrees C 110 degrees C can be predicted using this relation.